Hello, ladies and gentlemen. So now we're going to take a look at compound interest. Compound interest is interest earned on your current amount invested. That's a little bit tricky. Why don't we think about it as interest that earns more interest? So in compound interest, your interest earns interest, not just your principal. So here's the same idea. We've got Carlos walking into the bank, and he's coming in with $1,000. So he's going to put $1,000 in the bank. He doesn't earn any interest as soon as he puts in the money. I'm not sure why that has a degree sign. Let's get rid of the degree sign. So he's got absolutely no interest at the very beginning, but he deposits $1,000. Now, after 1 full year of that money being in there, he's going to earn $100 in interest. So then he has $1,100. But this is where it gets interesting. He now earns 10% on this amount, which is $1,110. So his $100 earned 10% interest, which is that extra $10 there. So now what he has is $1,210. So his interest that he earns on this is going to be $121. So then that is going to go over here. Now I better start using my calculator. I'm going to get $133. I can't count. This is $1,210, and he's going to have $1,331. And then that's going to change into 10% of that. Let's see if I did that right. So I had $1,100 times 10%, which is that. So I add that plus my $1,100, and that's what I got. Times that by 10, and I get this. So add that to this, and I get that. So now I've got $1,333, $133.10, and then that gets added, and that should be $1,464.10, and then 10% of that is $146.41. And that should be $1,610.51. So as you can see, our interest is earning interest and gave us a larger amount of money with the same interest rate over the same time, but this was compounded annually, meaning that interest earned interest as this goes along. Now, is this going to be linear or exponential? Well, we take a look at our differences, and you're going to notice that these differences is 100, this is 110, this is 121, this is 133.1, and this is 146.41. So no, the first differences are not the same, which means it's not linear. How can we prove that it's going to be exponential? Well, the ratios of these two need to be the same. So that's 1.1. So let's check that. 1.1. Let's check the next one. 1.1. Let's check the next one. 1.1. And the last one's going to be 1.1. Which means that they have a constant ratio between the y values. So if that's a constant ratio, that by definition is exponential, which means that our formula that we come up with is going to have something up there, we're going to have an exponent in our formula. So develop a formula, write an equation. I'm not really interested in this equation. Well, for this one, this equation would be, if we think about doubling time, the ratio is 1.1, the number of years is n, and our initial amount is 1,000. So that's certainly a way that we could come up with this equation quite easily from what we've learned before about exponential growth. So this is your growth rate, and this is your elapsed time divided by the growth rate factor, which is 1 a year. So for a formula, the formula that we're going to use is going to be the amount is going to equal the principal 1 plus I to the n, where n is going to be the number of years. Actually, in this case, it's going to be number of compounding periods, and we're going to talk about that more as we move on. And this is going to be your effective interest rate. And at this point, that's going to be the 10%. And we can see that in this 1.1, because that would be 1 plus 0.1, which is the 1.1. So let's flip over and do a couple of examples using our formula. So our formula is the amount of a loan using compound interest is the principal times 1 plus I, the effective interest rate, times n, the number of compounding periods. So we need to figure out what's what. So in this case, the principal is 5,000. The I is 3%, but that has to be changed to a decimal. So that gets divided by 100, so decimal 0. I better do it to make sure. 3 divided by 100. Yep. Decimal 0.3. And n is going to be the number of times that interest gets applied. And interest gets applied every year for 5 years. So that's going to be 5. So your amount now is going to be 5,000. 1 plus 0.03 to the 5. 5,000. 1.03 to the 5. Using your calculator in the order of operations, 1.03 to the 5 times 5,000. And we get an answer of 5796.37. So we can do that again. Angela is going to invest $200 that earns 0.5% per year compounded annually. How much will she have at the end of 20 years? So the amount is the principal, 1 plus the effective interest rate times the number of times that it's going to be compounded over the life of the loan. So in this case, our principal is 200. Our interest rate is 0.5%. So changing that to a decimal is 0.005. Remember to change that to a decimal. And it's going to be compounded every year for 20 years, which is 20. So A equals 200. Now I'm going to be smart here. This 1 plus I. I is this, so I'm just going to put a 1 in front of here. To the 20. And I'm going to use my calculator. 1.005 to the exponent 20 times 200. And it's going to be $220.97. Now, there's actually a little bit more of a penny here. What do we do with this amount? So, if it was normal math, we'd round up. But because this is money, the bank isn't going to give you that little piece of a penny. No way at all. Now, if you owe the money to the bank, then the bank is going to say that you have to pay them 98 cents because you owe that little bit of a penny and you can't go smaller than a penny, so they're going to call it 98 cents. But if it's money in your bank account and it rolls out to that, then the bank is just going to forget about it. It's not going to give you that little bit. It's going to say, hey, I can't give it to you. We can't give you anything smaller than a penny. And the most you're going to have in your account will be this. And that's just the way things work. All right, guys, there's 2 practice questions. Off you go.